This is Sarah Hojati with Lab 7, Mass of a Black Hole. The objective of this lab was to determine the mass of the black hole using the known mass of a star orbiting the black hole. In conclusion, my mass of the black hole came to be 3.76 times 10 to the power 31 kilograms. We were given the initial conditions from the lab. The mass of the star was given to be 1.989 times 10 to the power 30 kilograms, and the black hole was at the position -2 times 10 to the power 10, -2 times 10 to the power 10, 0. The time interval was equal to 1 day, or 86,400 seconds. We then had to import the velocity from the CSV file given to us in the assignment. Now, onto the while loop. The while loop tells the program to complete the following calculation through all of the CSV file from the first data point, which is at index 1, to the last data point. So we get the v final, which is at the index, and the v initial, which is at the index -1, so the previous index point. Using our data for velocity, it is easy to solve for momentum using p equals mv. Next, we wanted to split up the momentum into its components and use the momentum principle to solve for Fnet. First, we wanted to find the change in momentum over time, the dp dt, and then by applying a modified version of the momentum principle, we found that dp dt is equal to Fnet. To find the components of Fnet, we solve for dp dt in its parallel and perpendicular form and set that equal to Fnet. To find the components of Fnet, basically, we know that dp dt parallel is equal to the magnitude of the change of momentum divided by the change in time, all times the unit vector or the direction of the momentum. That is equivalent to Fnet parallel. And to solve for dp dt perpendicular, which is equal to Fnet perpendicular, you subtract the parallel component of dp dt from dp dt, since dp dt parallel plus dp dt perpendicular is equal to dp dt. So now with all of these components, we are able to model the problem. The black arrow shows the dp dt perpendicular to motion. The blue arrow is going to show the dp dt parallel to motion, and the red arrow is going to show the net force. So the model is right here. So this is the model, and as you can see, right here is the printed mass, and I'm going to show you how you can solve for it. Because we have all of the variables, all we have to do is plug in to solve for the mass of the black hole. So we just use the formula for gravity, which is g times the mass of the star times the mass of the black hole divided by the magnitude of r squared. R is the distance between the black hole and the star. And then we manipulated the equation to solve for the mass of the black hole. And from this, we got that the mass was 3.708 times 10 to the power 31, which was correct. So for the what does this mean question, this means that the value of Fnet and dp dt are equal, just like the values of the perpendicular components of Fnet and dp dt are equal, and the parallel components of Fnet and dp dt are equal. However, what these represent vary. So the value of dp dt is determined from observation and only signifies a change in momentum over time. And it doesn't really tell us anything about the cause or anything besides being a number. On the other hand, the cause of the change in momentum is represented by Fnet, and it tells us how the surroundings work on the system. So for the what if question, if the black hole whose mass we found was replaced by a different black hole but still placed at the same location, assuming that the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole, would you be able to tell the difference And no, we could not determine the difference because we calculated the mass of the black hole using the values of force, the mass of the star, and the distance between the star and the black hole. So none of these variables are changing in this situation because the motion is unchanged, so we would not be able to tell the difference between the two black holes.